Well, let's begin. So this is going to be our second lecture on event simulations and Unit 6. Okay, so we've finished Project 1, I believe. Is that right? And we're going to dig into Project 2. We've got a few weeks to do that. So let's just recap that. I can do that. Oh, I've got it right in this computer. Sorry. Might as well just show that right now. So Project 2 is due at the end of week 12. So we got a couple of weeks to get there, but what we're going to try and get launched into the basics of how to build an event simulator and the kind of generic one that you need to complete Project 2 in this lecture. And then later on, we're going to circle back and we're going to fill in some of the mathematical details, some of the optimizations you can do in Julia and this kind of thing afterwards. But here we'll get a good grounding of event simulations, discrete event simulators. We're going to see, we're actually going to iterate. We're going to do 3 different discrete event simulators this lecture. So hopefully you have a little bit of experience. And oh, thanks, Yoni, for the haircut. Thank you. Yeah, get a little bit of experience seeing how these things work and so on. So yeah, over the next week, yeah, and then after that, obviously we'll move on to Unit 7. So yes, last week before the break, we covered some of the basics of random number generation and what Monte Carlo was. So just to recap, a discrete event simulation is generally sort of a subtype of Monte Carlo style simulations. Usually they involve some variety of randomness. You could do a deterministic discrete event simulator, but I'm not sure what use it might be. So when you have a discrete event simulation, what that means is that events happen at instants in time. At T1, there's an event. At some later time, T2, there's another event, and then another event at time T3, okay? And the events happen in sequence, and there's some state, the system's in some state, and between events, the state doesn't change. And at the time of the event, what an event is a change of state, okay? There might be other kind of meta events for like when the simulation starts and ends and we want to do some logging and things like that, which we'll talk about later. So let's just talk about a really simple example. We're just going to make up an example. Hello, I'm sorry about that. So just to recap, we're going to do a call center that rings people and asks for donations. There's going to be 5 operators or workers. We're going to look at what they do over an hour. How many calls do they answer? How much money do they get donated and that kind of thing. Okay. So that when you call someone, or when there is a phone call, in this situation, the duration of each call is exponentially distributed. Some calls go very long, some are very short. And the mean of the exponential is 7 minutes. And for short calls, people just say, nah. If it's less than 1.5 minutes, we're just going to assume nah, they're not donating anything. And longer phone calls result in larger donations. So if it's larger than 1.5 minutes, we're going to assume the donation is proportional to 2.5 times the amount. Now this could be another random thing, but at the moment we're just making it a deterministic function of the duration. So there's lots of different ways of creating a similar situation, but we'll just give a simple example. So we want to look at the revenue as a function of time. You know, it's some sort of curve that we want to put in a plot. And when I scroll down a bit, we'll see it. And we're going to create a simulation that gives us that. Okay. So these kind of simple simulations are things you can approach analytically. This one is a compound Poisson process, and it can be a lot of statistics about what's going on in this process can be done analytically. Okay, so we're going to actually run a simulation, and throughout this lecture, we're going to compare our results to the analytical results and see how we're going. Okay, so I've got some code here. What it does is it's going to create a few realizations or trajectories of what might happen depending on the random numbers. Okay, so sometimes you might get lucky and you might get more donations. Sometimes you might get less. It's sort of a roll of the dice. So we're going to use a few packages. You're probably familiar with these. We covered distributions and random last lecture. Plots we've seen throughout. We're going to set the random seed to 0. We do this, remember, the seed is what the random number generator starts at. So this makes every time we run this code, it gives the same result. It's still making random numbers each time. It's just giving the same random numbers every time we run it. Okay. We're going to create a function. This is the short form for creating a function. So when you call duration, it's going to give you a random exponential distribution with a mean of 7. Okay. And the money made during the call is a function of the duration, and it's this equation here. So if it's less than 1.5 minutes, it's 0. Otherwise, it's 2.5 times the duration, $2.5 per minute. So, or maybe it's $2,500 per minute. I don't know. So the simulate function will run one of these realizations or trajectories. Okay, so you call it, and what it will return is a log of events at different times and how much revenue we've made at those different times. So that's what we're aiming to create, sort of a log of events. Okay, so we initialize the simulation with all the workers starting on a call. Okay, so maybe that's not realistic. You could make this more complicated. At t equals 0. We got some events that are happening. So an event at this point in time is just a number. That number means the time that the call ends. Okay. That's fine. The revenue, we haven't made any revenue in time is 0. We've got these two logs. So these are the results of the simulation. We're going to put things in these arrays as events occur. Okay. So while true, so we've got this infinite loop that keeps going. There's a break in here, so don't worry, it won't eat your computer. When the worker has finished a call, we want to deal with that event. Okay. So there's 5 people at the t equals 0. There's 5 people on phone calls. We find argmin. So this, you can think of this as find min. So it finds the index of the argument, which has the minimum value in event list. Event list is an array with 5 numbers in it. Each number is the time that operator is going to finish the current phone call that they're currently on. Okay. Okay, so we find who's the first person to finish. I is the number of the operator or the worker. Okay, so we get the time. We advance t. So remember, t started at 0. Now we're going forward in time. If it's more than 60 minutes, more than an hour, we're going to finish our simulation. So there's always going to be some logic in here about something has to terminate the simulation, otherwise it would go on forever. Okay, so we put in this last event at time equals 60. So we're not going to count this event because it happened after the hour. So we're just going to push an event at 60 so that there's a dot on the plot. So we have a pretty plot. Okay, and we haven't changed the revenue. The revenue stayed constant because the phone call hasn't finished. Okay, assuming that doesn't happen, a phone call's finished. We recalled the time that it's finished. we calculate the money made and we add it to our revenue, and we record the new amount of revenue that that we have at this time. Okay, and then that worker I has to be put on a new call, right? Which was called current worker calls. So this is this one. So this is the duration of the call people are currently on. So we give them a new phone call. They ring up someone straight away. It's random what they get out, and the this event list. If we're at T and the phone call is going to take a certain amount of time, we add that to the time, and that's the time that that phone call is going to end. Okay, so there's a pattern we're going to see throughout. Is when an event occurs, is when we actually start calculating a lot of things about the next event. Okay. Here we have a helper function. I don't really want to talk too much about it. What it's doing is we have a bunch of events. So we have times and revenue amounts. And this is a step function. So it's going up like this, right? In a step kind of way. And we want to plot it as steps. So what we're going to do for every event, we're going to first put the revenue in just prior to the event and revenue just after the event. So that when we plot it, we get a step function instead of a bunch of diagonal lines. Okay. So now we plot these stitch steps for each simulation in 3 different colors. And we get this plot here. So here's the revenue. Over the hour, we've made some of the order of $600. But depending on the realization or the trajectory, it's happened slightly different. You know, you might have had, here there was a time where all the operators were on phone calls for a long time. And then they made a lot of money at the end. Okay. So this is a kind of a simple discrete event simulation. I mean, I'm not going to claim it's particularly fascinating, but that just gets us through the kind of things we need to do in a simulation. Okay, so what we can see at every point in time, the simulation state is modified. Okay, and there's a state change, and these are like, you know, instantaneous deltas. So if you're a physicist, we're talking about like impulses and delta function kind of changes to the state. Okay. So these kind of simulations, they're suitable for lots of different things. You'll find their applications in logistics and social service and communications, but also they are used in physics. So for example, one example I really love is this example. I'll put up this video. So we're looking at the kinetic model of an ideal gas. So an ideal gas, we sort of have these. Okay. That is quite bizarre. Yeah. So here we have a blue gas and a red gas, and they've removed a barrier between these two gases. Okay, and it's just a simulation. It probably looks quite fuzzy online because of the video compression. It'll zoom in a moment, but it's basically, you have thousands and thousands of interactions where these different balls of this ideal gas are sort of bouncing into each other. Mostly they're traveling in straight lines, you know, with constant momentum. They hit the walls, they run into each other. And when they do collide or hit a wall, that's an event, okay? So, and here though, at a particular point in time, they remove the wall on the left and the gas is flowing out. So this is one way of simulating, you know, the pressure and temperature distributions in a system. So yeah, I always like that one. Oh, this one has loaded now. That's all right. I actually implemented a toy one of these during my PhD as a side project. It was kind of fun. I think it'd make a kind of cute computer game, edutainment game where you know, have to make a heat engine or a refrigerator or something, moving pieces. I think it'd be fun. But yeah, these things are used in real research to simulate, you know, study phase transitions, chaotic systems, and this kind of thing. But these do come up in serious work. So back to logistics applications, we're going to run through a bunch of examples in this kind of field in this course. Okay? So it's going to be all these different queues, different things waiting for other things, this kind of application. All right. Cool. This is just excellent. So what's on that? Good. So we're going to look at another example. It's going to be a little bit more complicated. We're going to work our way towards examples closer to what you see in Project 2. There's also a tutorial class which has the similar focus, working through yet another event simulation similar to Project 2. So you and your partner will be able to look at all that and sort of put all the extra pieces missing to do the complication in Project 2. So in this example, we're going to look at a health clinic. Okay, so there's a waiting room of patients. There's doctors waiting to see the patients, and there's a secretary that has to deal with payment. So when we look at any moment in time, what we know about the system is called the state. So if we look at an instant in time, in a system like this, you're going to know things like the number of patients in the waiting room, number of people talking to the secretary. So she's probably, he or she would only be able to deal with one person at a time. So it's 0 or 1. The number of patients engaged, who's engaged with which doctors. Some doctors may have other activities like being on breaks or otherwise engaged, not engaged. And again, whether the secretary is busy or not. So generally in an event simulator, you always have this state. Okay, so the state is just data about what's happening at the system point in time. The state stays constant, and when an event occurs, the state changes discretely. It's a discrete change, an instantaneous change of a certain magnitude. So it's not a continuous process like a differential equation. So some of the events that may occur to change the state is a new patient could arrive in the clinic. A patient might enter a doctor's room. A patient might leave a doctor's room. And at that point, they're meant to go see the secretary and pay. And the secretary may answer phone calls or complete a phone call or deal with a person, so on and so forth. Okay. So this is a kind of, it's a simple but somewhat realistic model. So you know, you might be interested in this kind of thing if you had like, you know, a pop-up COVID clinic, and you might want to kind of have some idea of how many staff you need to put on to deal with your expected intake of people and this kind of thing. So these kind of models will come up in real life. Okay. I think my YouTube is talking. This is hilarious. Okay, hopefully that's not causing problems for people at home. All right. Okay. So, you know, and to perform this kind of simulation, you know, you have all these events that are happening T1, T2, T3. But the point is, how do we figure out when the next event occurs? And the current state of the system depends on all the past events, and the future events or the next event mostly just depends on the current state. Okay. So, for example, an event, a patient leaves the doctor's room, goes to speak with the secretary, and this type of event will only occur after someone's been in the doctor's room. Okay. And it's implemented, you know, it's scheduled generally when the person enters the doctor's room. You have an event, someone enters the doctor's room, and at that point you create the event for them leaving. Okay. And hopefully in the simplest cases, you can actually figure out the time and most of the properties around that event before it's occurred. Sometimes it's more complicated. What happens when the event occurs might depend on the state later. So you might have to do calculations later. Or in the worst case, the duration until the next event might depend on state changes in between, in the intermediate time, you know, depending. on things. But still, hopefully you can efficiently deal with that and update the state and the set of events as you go, if that's the case. Okay, so you generally have an event schedule. So in the previous example, the event schedule was basically like this event list, which was a number for when each person was next finishing a call. And you'd have a sort of state as well. Okay, so the simulation just jumps from T1 to T2 to T3 and so on. Okay, hopefully I'm not belaboring the point here, but I just want to make sure that there's nothing unclear about this, the really fundamental piece of this simulator. Okay. So it's probably worth pointing out that if you're doing this sort of stuff commercially, you're quite likely to be using a commercial software package. AnyLogic, Arena, and GoldSim are some of them. I've never used any of these packages myself. I probably haven't really been involved in use of that kind of work. Although at the startup that I'm working at, we have our own event simulator, and we do these kind of simulations ourselves. So I guess that's relevant. All right, so that discussion was a little bit hypothetical, a kind of a situation you might want to have in your head. But here's one we're going to solve again on the computer here. It's a bit more complicated than the first one, but not very complicated. So one of the most simple examples to consider is just a queue. So you have a bunch of customers or whatever jobs waiting for something to happen. And it's called a queuing system. And queuing theory is a well-studied research field. And you can cover this in Stat 3004. So I'm not terribly familiar with that class, but I know Yoni is. So, okay. Right. So the simple example I want to just look at here is something called an MD1 queue. So these letters I'll explain in a minute. So M is talking about the arrival events. So the arrival events to the queue is Markovian or memoryless one. So it's a Poisson process. So Poisson process occurs when there's a bunch of events, like people turning up to a fever clinic is a Poisson process, because all the different people that turn up, they will independently decide to go or not go. They're not going to change their mind of going or what time they're going based on what other people are doing. It's sort of an independent set of people turning up to the queue. Okay. So yeah, and Markovian's kind of like the technical term for when we have a memoryless or a stateless kind of operation like that, where it doesn't depend on just what everything else is happening. D in this case is the duration, is a deterministic duration in the queue. Okay, so D for deterministic. This could also be another Poisson process, so M or something else. So there's MM1 queues, for example. And one is there's a single server. Okay, so an MDK queue might have K servers, like you'd have a supermarket with K checkouts and a bunch of people turning up and being served. So a lot of these sort of simpler MD1, MM1 kind of queues, there's a lot of analytical results around that. We're not going to really delve into that, though we'll show you the formulas to compare. The kind of things you're interested in these kind of systems is the system stable? So an unstable system might be one where the number of people in the queue diverges to infinity. You think of, again, an event simulator like coronavirus. A virus population might become extinct and head to zero. It might stay steady at a certain level, or it might sort of diverge to infinity and kill all the humans or something. So that's sort of a basic question. Is it stable? Does it have fixed points? What kind of steady states does it have? What kind of distribution do those steady states have? What kind of dynamics do those steady states have? Dynamics like how long are people waiting in the steady state, things like this. And then, but then there's also transients. If you start with an empty queue, you know, how long does it take until you reach the steady state? Things like that. For simple systems like MD1, like I said, there's analytic formulas. But we're going to look at the MD1 queue here, and also two variants, MM1. So that means the duration of the queue is also a random Poisson variable. And MM1K, which is that there's actually K queues. Oh, sorry. No, that's an extra slash. I apologize. MM1K is that there's a finite queue capacity K. So once the queue is full, it doesn't accept more people or more items onto the queue. Okay. Which you could model as a different kind of event. There's another way of thinking about that as well. So normally we you know, formulaically we look at these variables, rho, lambda, and mu. So lambda is the rough time it takes for the arrival rate, and mu is the service rate. So one of them is the service time, mean service time. And rho is the ratio of these two things. So if you have a high arrival rate and a slow service rate, you'd expect queue growth, and vice versa. If mu is greater than lambda, you'd expect the number of items in the queue to decay. Yeah, then there's this K for the MMK. So here it is. This is going to be a queue simulator. So what we're going to do is I'm going to show you another implementation, just like the first one, where we've hard coded everything we need to do in the simulation into this event simulator. When we're done, we're going to write it a second time, but generically, where it's an event simulator that could simulate just about anything. Okay, and we're going to use that generic event simulator and implement the same system again. Okay, so let's just dig into this one. So this is like a hand-coded thing. You know, if you're on a project and a client or someone asks you to do this kind of work, or you're doing research, you can always follow this approach, and it's perfectly fine. And you'd never go and write a generic simulator or something until you've done this kind of thing several times and you know what you're doing. Okay, so let's have a look at it. So we've got, again, the same sort of includes and seeds and sort of stuff at the top. And we've got this Q simulator function, and at the bottom we're calling it. Okay, so let's have a look what the Q simulator takes. It takes T, so T, the capital T is the final time. So the previous example was 60 minutes. So it's when does the simulation end? There's always going to be some end. There's arrival function and service function. So we're not actually passing numbers into this. We're actually passing functions, and we're going to call those functions inside the simulator to give us, say, the time between arrival events, which is the arrival function, or the time it takes to provide service, which is the service function. So this way, if we look at service function, this could be deterministic for an MD1 queue, or it could be a Poisson process for an MM1 queue. And then capacity, that's equivalent to the K for the MM1K queue. And then the initial length, how many things are in the queue at T equals 0, okay? So we start off at T equals 0, we start the queue with an queue, and we're going to create what's called the queue integral. Probably not a great name. So at the end, it gets divided by time. So what this is it should be it should be the mean of queue size over time. That's what it represents. Probably should rename that for next year. Yeah, but that will be the mean queue size by the time we're done. Well, when we return it here, or what we return is the mean queue size. Yeah, that's fine. All right. So here we are calling this arrival function. So something's coming into this, and we're going to call it. What this should return is a float 64. Okay. We could annotate the types here. Functions in Julia don't have specific, like they're not typed with the return type because they're all generic. But you could like annotate this with float 64, so it throws an error if it gets something unexpected. And the next service, well, depends whether if the queue's empty, there is no next service. We just send it to infinity. That's just a convenience thing. That event will never actually occur. or if the queue is not empty, we have to figure out what time it is that that service will be completed. Right. So while time is less than t, we're going to repeat this loop over and over again until we're finished. We're advancing time, so we're and looking at the previous queue thing. That's fine. So this is just a record of the previous time. We use that down here in this integral. So if next service is less than next arrival, so if the service is going to finish before the next person arrives, then the next event is a service completion event. Okay, all right. So we advance time to the next service. We subtract a person from the queue because they've been served. If there's more people still left in the queue, we create another next service event at a time, the current time plus service function. So again, we're calling a function, it's going to return a number. So this generic function doesn't know what this is going to be. We're going to be able to build multiple simulations out of this one function. Okay. Otherwise, next service is infinity. Now, why we use inf here and not something else is because that means this predicate, this less than, is always false. You're always going to arrival events. Okay. So it's just it's kind of a neat little trick in a way. So if there's no one here, you might argue that there is no next service, but it's just as valid to say the next service is infinitely far in the future, so that the next event is an arrival event. Okay. So if the arrival time was smaller than the service time, we go down this branch. We set the time equals arrival, and if the queue is less than capacity, we add someone to it. If the queue was empty, we have to handle the case. So if the queue already had people in it, you're not going to be served next. You've got to wait your turn. But if the queue was already empty, we have to create an event for you being served, the finish of your service. Okay, because you'll be starting to serve straight away, but it might take some time. Okay, and again, we have to queue up another arrival event. Okay, queue integral. So here we're integrating, basically it's the integral of t times q size, right? So if you think of this as, again, another step function, we're integrating the step up to the current time, which is why it's q previous. And then at the end, once we've finished going for t, we divide by the time. Now, I noticed it's probably a little bit unneat at the end. It probably could, at the end, do the integral between small t and big T as well, and divide by big T, but it doesn't. So that's fine. It's approximately good enough. Here are the numbers I was speaking about earlier that parameterize the simulation. We're going to have an arrival rate of 0.82. So every unit of time, 0.82 items arrive. If you're curious how do you create a symbol like lambda in your REPL or whatever, all you do is you just go like / lambda and then type tab, and it will kind of give you the character. Okay. Mu, so this is the rate that people get served at. It's a larger rate, so people get served faster than they're leaving. So the rate is 1.3 services per unit time. For the MM1K simulation, we're using K plus 5, maximum 5 items in the queue. The ratio here is there, and the time we're going to simulate for is 1 million. Okay. That's fine. Okay, and here are the theoretical results. I'm really not going to go into this, but basically, you can see there's a nice simple result for the double Markovian version. It's very trivial to derive that. There's a slight correction for MD1, so it's actually weird that having this deterministic thing actually makes the analytical stuff a bit more complicated. And the MM1K theory, again, it can be solved analytically. I just don't want to talk about it. So, and then here's the estimates we're getting from our event simulator. We're going to run the Q simulator. So this is for MM1. So both arrival and service events are Poisson processes. So the duration of time in between Poisson events is an exponential distribution. I mentioned that for the break. So we're simulating for a time t, and the service, the time to the next arrival is given by this exponential of 1 on lambda, and the time between sorry, arrival is the first one, service is this one. Okay, so the MD1 service is always equal to this number 1 on u. Okay, it's always exactly 1 on 1.3, so a bit less than a minute time. Okay, otherwise the mean of these two distributions is the same. And MM1K, we've got this extra element K. Remember over here, the third argument here has a default argument, a default capacity of infinity. Okay, so it never triggers. So if we can actually run this simulation and compare these 3 theoretical results to these 3 simulation results, and you can see over a million time units, the system sort of comes to equilibrium, and we simulate it long enough that the mean number of items in the queue is approaching the theoretical results. Okay, so there's some level of fluctuation in like the 3rd digit there, but it's pretty good to like 1 in 1,000 or something, 1 part in 1,000. So if we simulated for time 1 billion or 1 trillion, the accuracy would go up. The simulation would take longer. So generally speaking, the accuracy of your simulation is going to go with the square root of the amount of effort you put in, or 1 on the square root of the simulation time in this case. Okay. There's some transients to account for here too. All right. Cool. So yeah, so what we've done, as I mentioned, it says here, we've averaged over time rather than doing lots of different trajectories and averaging many trajectories at an instant of time. We're doing this over time kind of interval. So it's an ergodic system. This system will come to some kind of equilibrium. Okay. It doesn't really matter what your initial, ergodic means it doesn't matter what your initial condition is. You'll always end up in the same state of equilibrium. Well, technically, ergodic means the system can transition from any state to every other state. There's always a path between any 2 states. And yeah, if you wait long enough, you will follow the path towards the stationary state. The stationary state is a distribution of states. Okay. So this is usually a more efficient way of doing things, but you do have to be careful about all those transient behavior that's happening with the initial part of the simulation. So if I was going to improve this, we might run for time 1 million, but we might want to throw away the first 1,000 seconds, let's say. Yeah. So, all right. So that's fine. Are there any questions? Lots of questions up here. Where are the queuing theory? Where are the queuing theory formulas for? Oh, okay. Oh, good. Thank you. Good. Yeah. Look, seriously, if you have any questions, please chirp in. Okay. So this is a particular example where there's particular types of events, and the state is pretty simple. It's just the number of items in the queue, really. That's just the only real state. And the events are like what's happening next. So there's only basically 2 events: the next arrival and the next, the next arrival and the next termination of service. There's another thing. There's 2 other things we've snuck in here. They're kind of secret events. One is relating to ending the simulation, and another secret event is relating to this integral. So calculation of the results. So what we're going to do now is take a more structured approach. It's going to be more generic. We're going to just rely on the fact that we have a simulation, and a simulation has state, a simulation has events, and we're going to simulate it. Okay, and we're going to write a generic function that doesn't care what the state is, doesn't care what the events are, but it can still work. Okay, All right. Let me just take a drink before we continue. We've got 20 minutes for this. Excellent. So this is going to be a more generic one. You're going to implement your own generic one to deal with basically more queues, multiple queues. So let's have a look what we got here. We have an import statement. I'll explain why that's it. We have this is where the action's at. We're creating two abstract types, event and state. Okay, so this is the syntax in Julia to create an abstract type. Now you can't create an event or a state at the moment. There's no concrete examples of event or state yet, but there's a sort of a type tree. These things can be the super type of things we're about to define. Okay. We're going to talk about a timed event. So an event is something that occurs. A timed event is something that occurs plus the time that it occurs. Okay. So we compose two bits of data together in a struct. I assume you've all seen struct before, but basically you're creating a data type that has two fields, event and another field called time. We're just assuming time's a float 64, which is generally good enough for these kind of simulations. Although sometimes you might want to use an actual date time. If you want, what we've got here is this function called isLess. Okay, so remember when we have many different events to choose from, we have to choose the event which occurs first. So events, timed events, have a natural ordering depending on time. Okay, so what we're saying is this comparison of two timed events, which one occurs first, is just done by comparing the time fields. Julia has two functions for comparing things. One is this less than symbol, and one is this isLess function. They're not identical. They differ very subtly with cases like nan, if you remember nan, okay? So, the IEEE standards for less than of nan, or comparison of nan is always returns false. What we're going to do is we're going to put these events into heaps and structures like this, and we don't, those kind of structures, they want to deal with the ambiguity of things maybe not being equal to themselves or not being less than anything else and things like that. So we define this isLess function. Okay, and that is a generic function that data structures will use, that will be used by data structures. So by doing this, we're actually able to create, able to use some of the functionality in data structures with timed events as the elements. That's the point of that. Okay. So here we're going to create a function. Function's called process event. So what its job is to give an event, given the current time, given the current state, and some event, which is the next event, the event that's occurring now at time, do something, process that event. So if that event is someone was served, what this function will do, process event function will do is remove someone from the queue, right? Because they were served. Or if the event is someone arrived, then you take the queue length and you would add one to it. So this function is going to mutate state, and it's going to return new events. Okay, so some events, they just happen, nothing else happens afterwards, they're just finished. Some events, like the Poisson process, you have an arrival. Once that arrival occurs, you draw again from the exponential distribution to figure out when the next arrival is. Okay, but there's nothing stopping an event occurring, an event creating two events or three events or n events. So what this function will do in general is its job is to return an array of timed events. Okay. Now, there are some things which are part of every simulation. The simple simulations have to end, or they don't end. They're not very useful. So we're creating this end sim event. This is just a short form. Normally structs have fields. This struct has 0 fields. So when you put it in your computer, it takes 0 bytes. When it's compiled code, because Julia can figure out the runtime through the type at runtime through type inference. It can completely remove any overhead associated with creating these objects. You know, it doesn't need to create an NSIM event object when you tell it to. It just says, okay, there's this thing that I'm imagining it's this, and that's called a singleton type in Julia. Okay, so what we've got here is we've got this generic function. Now, what the idea of this thing is that we're going to overload it. So we've defined it with 0 methods here. We're going to add methods to it depending for different types of events. Okay, so for the NSIM event, we're just going to log to stand it out that the simulation is ending. Okay, and it doesn't return any more events. Okay, we'll deal with it a little bit more later on as well. There's also log state events. So this is creating the results of the simulation. So what this does is it simply prints the results to stand it out. Okay, so it's not particularly fancy. You know, you might want to keep it in memory or write it to a JSON file or a CSV file or something to look at the results later. But yeah, it's good enough for our purposes. All right, so now we're going to look at how do we use process event. How do we use the process event function to build a simulator? Okay, so the main simulation function receives an initial state, the first event. Okay, again, we could tweak this so it takes an array of initial events. If there were no events in it, we'd sort of just end straight away, right? So in this example, there's always a seed sort of event that creates all the rest. And then there's these keyword arguments. So if you have a semicolon and a function definition, everything that's after it are keyword arguments. They're optional. They always have a default value. Well, they're not anymore. You can make them mandatory now. So the max time, so that's when does the simulation end. A vector of times for when to do the logging. Okay, so maybe you want to run for 100 seconds and create a log every second, and then you have 100 loggings. And then there's this magical thing called callback. Okay, so it defaults to this function. This is an arrow function. It's a very boring function. It just always returns nothing, so it doesn't do anything. It doesn't return anything. But you can use it, and what it can do is it can do things like that integral we did earlier. It can given the time and the state, it can edit some other state that keeps track of the results you're interested in. So in this way, you can integrate things. You can calculate like mean times in Q and various things like that. Okay, so this is all very abstract, right? So that's kind of cool thing about this is it's actually going to work out, but currently we're not really talking about anything concrete at all. So we have this priority queue, which is a binary min heap. In a future lecture, I'm going to talk more about this. Basically, rather than searching through all the events, figuring out which one's next, we're going to use a heap, and the heap will efficiently tell us if there's n things in the heap. It will tell us in constant time which is the first one, and if we add and subtract things to the heap, it doesn't take its constant time as well. So it's very fast structure for this kind of simulation. It's sort of the standard go-to data structure that would be at the heart of an event simulator. Okay. There are some default events we add. There's an initial event that I said that always gets provided as a seed. In this case, I think your simulator might be a bit more generic. You might accept an array of these things. There's the simulation event at the end. So there's an NSIM event at max time. And then there's all these logging events. Now, that basically initializes the queue. Okay. What we're doing here, there's an initial state. Now we do a deep copy because I said that process event function, it's allowed to mutate in the state. And people are going to want to call this function more than once. So what we do is we create our own copy of the state, and then we mutate it. And what was sent to us, we haven't changed. We're not writing to it, we're not editing it. Okay, so deep copy is a generic function. It just it copies everything. If it's an array of arrays, it'll copy all the way down to the leaves. Okay, and we start with time equals 0. At the time equals 0, we call the callback. Again, by default, this doesn't do anything, but it might be taking some information about the state. Okay. Here's a really simple simulation of group now. So what we do, it's while true. Okay, we get the next thing off the priority queue. So it's stored such that it's really easy to get the first thing, the next thing. We advance the time to the time of that event. We process that event. Okay, so does someone leave the queue? Does someone get added to the queue? Whatever. If the event was an NSIM event, then we break. So that while true is kind of dangerous. Something has to break it. And so this always gets added. Yeah, so it's generally safe so long as max time isn't nan, basically. The final thing is these things, the process event might spawn new events, another arrival or a service event or something. So for each of those, we put them in the priority queue. So for the next time events, new time event and new time events. Yeah. And then again, every time we iterate, we're going to call this callback function. Okay. So this thing could be used for almost many applications. The only thing to make it more generic, I would think to do, is to make the initial set of events a proper collection. And then you could basically use it for anything, including project 2. Okay. So here we're going to talk about how we actually set up all the state and events so that it just works. So we're going to create the state. So the number of things in the system or in the queue is an integer. So it's a mutable struct that can change over time. Okay. So mutable, here's a keyword. It just means all the fields, they can be edited. Okay. We created 2 other types of events when something arrives, events when someone gets serviced. There's no data associated with those other than the time, and timed event already carries the time with it, so we don't need to put it in here. Okay. So you might have more complicated events where sometimes maybe you serve 2 people, so you might need the number of people being served, that kind of thing. So these don't have to be empty structs. They could have things in them, basically is what I'm saying. For the arrival event here, what we're going to do is we're going to edit the state. We're going to put something, an extra item in the queue here. And we're going to create an empty vector, and we're going to put in it a thing for the time for the next arrival. So this is a Poisson process. So we're sort of hard coded that. It does depend on this lambda out here in the new. But this is a random function, right? So every time this process event gets called, something random happens. If it's the only job on the server, that means there's no current end of service event. So we put an end of service event in. Again, so here we've hard coded it with the deterministic. So this is an MD1 queue. And to process the end of service events, the number of items in the queue gets decreased by 1. Here we're just doing an assertion to make sure it's not doing something stupid with negative number of things, just to make sure we didn't make a mistake. And finally, depending on whether there's one or at least 1 or 0 items, we either add another end of service event or not. So we don't have to fiddle around with infinite events at infinity anymore, right? We have this general collection of events, and there is no next service event at this point in time. Okay, so it's an empty vector. All right, and now we can simulate it. Brilliant. Okay. So we can simulate it with an arrival event time at 0. We can log it times 5.3 and 7.5. I'm not sure why we chose those numbers. But okay, but it's basically telling you the Q state at these various times. Not much has happened. There's 3. I guess things have ended and left, and there's 3 things. Now I could bump up the number of log times here, and we could spam it all to the screen. But we'll just have a look at how the callback function works. So let's call this record trajectory. It pushes to a vector the time and the number of things in the system, and that's it. Okay. And we define the callback as record trajectory. And we're going to plot it. Again, we've got this stitch steps from before that turns these points into a step function for making the plot look nice. And now we can actually see a really nice plot of what's happening versus time. Okay. So here we can see that, at the time samples we had at the screen, it was 3 and 3 or something, but it's actually jiggling up and down all the time. People arriving, people being served, it's going up and down. And this has some sort of distribution, a mean, a standard deviation, this kind of thing. Okay, and there's some transient behavior that happens at the start because we will start at 0. So here we're going to not run a short simulation and plot it. Now we're actually going to use the callback function to do that integral. So add the integral. We're nearly at the end of this lecture, so I'm just going to skip over that. That's just doing as before. It's just finding delta t and multiplying it by the Q size, okay, and adding it to the integral. There's this global keyword here. Just be careful of this. Normally, when you create a function, it creates new variables, but you can tell it not to. You can say, oh, these variables here are the ones from the outer scope, and we want to edit those. We don't want to be setting ones in the function and forgetting them. We want to be remembering the things outside and editing them. Okay, so now we can simulate that with a different callback, okay, and print out what the mean Q length is, and it compares very favorably again to approximately percent or something. No, better than 1%. It compares favorably to the statistical, the theoretical result. And that's next lecture's content. So I timed that really well because we have 1 minute to go, I believe. So thank you all. There's no more questions. Does anyone want a question for the last minute, or shall I see you on Monday? Okay. Thank you very much. I hope that was informative. Yeah.